Hi everyone, welcome to the Physics Workshop channel. Here we make tough physics stuff easy and fun. If it is your first time, don't forget to hit subscribe and turn on the bell so you don't miss our cool tutorials. I'm Parham Fatemi, and in today's tutorial we are advancing our exploration of dynamics with a focus on rectilinear motion, straight from the Engineering Mechanics Dynamics 9th edition book. Rectilinear motion, the study of objects moving in a straight line, is a fundamental concept in understanding the dynamics of movement. It forms the bedrock for many principles we observe in the physical world. So let's dive into this vital area and uncover the mysteries of how objects travel along a straight path. As always, have your notebook and calculator ready. Feel free to pause and replay as needed. And if you have any questions, drop them in the comments below. I'm here to make sure you get a clear understanding of these concepts. Ready to get moving? Let's start our journey into rectilinear motion with our first problem. Here we go. Before we jump into the problems, let's lay some groundwork on the concepts we'll be using throughout tutorial 2. So, whenever acceleration is constant in any problem, we can use one of these three equations. So, you may be confused about choosing each of them. So if there is nothing mentioned in the problem about displacement, you can use the first one. So it's a useful hint for you. And whenever there is nothing mentioned about time, you can use the second one. And finally, when there is nothing mentioned about velocity or v, we can use the third one. So these three equations are very straightforward and yet very useful. But what about not constant acceleration? Because in real world, acceleration is not constant, right? So now we're going to talk about displacement, velocity, acceleration, and two superheroes of calculus: derivatives and integrals. Displacement is simply how far something has moved from its starting point. Now, if you want to know how fast that something is moving at any instant, that's where velocity comes in. And if you are curious about how the velocity itself changes, that's what acceleration measures. Imagine you are driving and your speedometer is your velocity. The derivative is like a snapshot of your speedometer at any moment. It gives us the acceleration, how quickly you're pushing the pedal or hitting the brakes. Now, if you've ever watched your odometer, that's where integrals shine. Integrals add up all the little bits of distance covered over time, which is essentially your displacement. When you integrate velocity over time, you get how far you've gone, your displacement. And if you integrate acceleration, you get the change in velocity. So think of derivatives as the magnifying glass that zooms in on a moment to tell us the rate of change, while integrals are like the wide lens that captures the entire journey to give us the total change. With these tools, we can analyze any motion, predict future movement, and understand the past path of any moving object. Ready to see these concepts in action? Let's start with question 1 and see how derivatives and integrals help us tell the full story of motion. Alright, let's dive into our first question about rectilinear motion. We are given a particle whose position over time is described by this equation here, right? Our task is to plot the displacement, velocity, and acceleration for the first 5 seconds of motion and determine when the particle changes direction. First things first, let's find the velocity and acceleration by differentiating our position equation with respect to time. So once again, this is our displacement equation. S equals 0.27 times t cubed minus 0.65 times time squared minus 2.35 t plus 4.4. So this is our displacement equation. According to what I mentioned before, we can find velocity by differentiating this equation. So v, or velocity, equals ds, or derivative of displacement with respect to time. So ds over dt. And now you can calculate this derivative, and it will be 0.81 t squared minus 1.3 t minus 2.35, and the unit here will be feet per second. For acceleration, we differentiate velocity, right? So a is derivative of velocity with respect to time, or dv over dt, and this one will be 1.62 t minus 1.3, and the unit here will be feet per second squared. And now you can plot these three equations. So this is v, and this is a, or acceleration. And looking, after you plot the equations, looking at the plots, we can see how particles' displacement, velocity, and acceleration change over time. Notice how the velocity plot crosses the time axis. That's our cue that the particle is changing direction. So when velocity comes 0, it means it's a change sign, right? Because whenever something is changing its direction, like this line, at this point, velocity is 0. So looking at the plot where the velocity is getting 0, it means our position, our direction is changing. To find the exact time when this change occurs, we set the velocity equation to 0 and solve it for t. So let me write it here for your notes. For a change in direction, velocity should be 0. To change sign. So using this equation here, we make velocity 0. Equation is 0.81 t squared minus 1.3 t minus 2.35. And if you solve this equation, you will find two values for t. One is minus 1.08. The other one is 2.69 seconds. But this one is not acceptable because it's negative. So we found the time. And there we have it. At about 2.69 seconds, our particle reverses direction. This type of analysis is crucial for understanding motion in a straight line, and it's just the start of what we'll explore in dynamics. How would this motion look like if we could see it in a real life? Think about it, and let's discuss it in the comments. That's all for this problem, and let's go to the next question. Let's tackle question 2 and see how integrals reveal the story of motion. This time we are given the acceleration of a particle as a equals 2t minus 10. And we want to find out its velocity and displacement over time. So this is our equation here. And acceleration tells us how quickly something speeds up or slows down. But how do we go from acceleration to knowing how fast we are going or how far we've traveled? This is where integrals come into play. They let us add up all the little changes to get the big picture. I'm going to explain integral one more time. So imagine acceleration as a series of tiny pushes to our particle. To get the velocity or the overall push, we add up these tiny pushes over time. In math, we call this process integration. It's like adding slices to build a whole loaf of bread. So we take the integral of our acceleration, which is 2t minus 10, considering the particle initial velocity is 3 meters per second. So here we have a equals 2t minus 10, and you know a is derivative of velocity with respect to time. So we can take integral. So from initial velocity, which is 3, to the final velocity, dv, from 0 to t, 2t minus 10 dt. This is how we take integrals. And by doing the calculation, you will find the velocity is 3 minus 10t plus t squared. And the unit here is meter per second. So this is our equation for velocity. Now velocity is great, but where is our particle exactly? Again, we use an integral. This time we are adding up all the speeds over time to get the distance, which is our displacement. We integrate our velocity to find that the particle's position at any time. So we can write the next integration like this. So we know that ds over dt, this one is v, right? Velocity equals 3 minus 10t plus t squared, which we just calculated. And if you take integral of this one, you can write from initial position, which is minus 4, to our final position, ds equals integral from 0 to t our equation 3 minus 10t plus t squared dt. And by calculating this integral, you can find the equation for displacement. S will be minus 4 plus 3t minus 5t squared plus 1 over 3 times t cubed. And the unit is meter because it's displacement, right? So this is the equation for displacement. And that's how integrals help us paint the complete picture of a particle's journey, from the rate of acceleration to the path taken. Integrals are our best tool for understanding motion. Now let's go to the next question. All right, let's dive into question 3. We are given a graph that shows how a particle's velocity changes as it moves along a straight line. Our goal is to find the particle's acceleration at the specific point where it's 20 feet from the starting position. So do you remember those 3 equations that I mentioned at the very beginning of the video? If you don't, I suggest you go back to that part of the video and come back to this question again. So we had 3 equations for non-constant acceleration questions, and one of them is a ds equals v dv. We're going to use this equation for this question, and once again I'm going to explain what is acceleration. And the reason I'm repeating these explanations is because if you understand them, understand acceleration, understand integration, then you can solve questions much better. So acceleration tells us how quickly the velocity of a particle is changing at a given position. It's the slope of the velocity position graph. But how do we find this slope? It's simple. We draw a tangent at the point of interest and look at how much the velocity changes for a small change in position. So on the graph, we find that at 20 feet here, and this is the tangent, the tangent line gives us a slope or acceleration, calculated by taking the change in velocity divided by change in position. So this is 20 feet, and the velocity at this point, according to the graph, is 3. So this distance here is 5, and this distance is 2. So using this equation, we can write A equals V times dV over ds. dV over ds is simply the slope that we have in the graph, and V is the velocity, and at 20 feet the velocity according to the graph is 3. The slope is 2 over 5, so we can easily calculate acceleration, which will be 1.2 feet per second squared. So at 20 feet, the particle's acceleration is 1.2 feet per second squared. This number represents how quickly the particle is speeding up or slowing down at that very point. Understanding graphs like this is crucial because they give us a visual way to understand motion. And remember, acceleration is not just about speed, it's about changes in speed. A positive acceleration means our particle is speeding up at 20 feet along its path. Now let's go to the next question. Now let's tackle question 4. Here we have a car traveling at a constant speed on a flat road. It hits a 6% incline and starts to slow down because the driver doesn't adjust the throttle. We are asked to calculate the car's speed after certain conditions. So here's a trick. whenever you saw a question like this, the first question that you need to ask yourself is that, is it a constant acceleration question or it's a non-constant acceleration question? Because if you find this, then you know which equations that you are going to use. So if you don't remember the equations, you can pause the video and go to that part of the video which I wrote the equations, and then you can use them for this question. So it's a constant, this question is a constant acceleration question. Why? Because here you can see it says the car decelerates at the constant rate g sine theta, right? So it's a constant acceleration question, which means we can use one of those three equations that we have. So first things first, let's convert the car's speed from kilometers per hour to meters per second for easier calculations. So it says here the initial velocity is 100 kilometers per hour. You can easily convert kilometer per hour to meter per second by dividing it to 3.6. So velocity is 100 divided by 3.6, and it is 27.8 meter per second, right? And the incline causes the car to decelerate at a rate of g sine theta, which we need to calculate. So acceleration is minus g sine theta. Excuse me, what is that negative sign? Well, deceleration is just acceleration in the opposite direction. Our car's deceleration is due to gravity pulling it down the slope, right? So that's why we use that negative sign, and it's very important. And yeah, here we're given that theta, the slope's angle, corresponds to a 6% incline. Using a bit of trigonometry, we can find the deceleration. So here, whenever it says tangent of angle is something, it means you can write it like this. So theta is arc tangent of 6%. So we have theta. Using your calculator, you can calculate this arc tangent. So for acceleration, we can write minus 9.81 sine arc tangent of 6%. And if we calculate this one, the acceleration will be minus 0.588 meter per second squared. So we just calculated the acceleration. For part A of this question, we want the speed 10 seconds after hitting the incline. Since acceleration is the change in velocity over time, we can multiply our deceleration by 10 seconds and subtract it from the initial velocity. This one is the equation that I mentioned at the very beginning of the video, which we can use whenever acceleration is constant. So V equals initial velocity plus AT, right? So we have the initial velocity here. We have acceleration. Here we just calculated. This is the initial velocity and the time is 10 seconds. So we have nothing about displacement. So that's why we can use this equation. So initial velocity is 27.8 meter per second plus acceleration, which is minus 0.588 times 10 seconds, right? By calculating this, you will find the velocity is 21.9 meter per second. So part A is solved. For part B, it asks for the car's speed when it has traveled 100 meters along the incline. This is a classic kinematics problem where we use the equation v squared equals initial velocity squared plus 2a times displacement. One of the other equations that I mentioned for constant acceleration questions. So we can write v squared equals initial velocity squared plus 2a times displacement. Again, we have everything that we need. Initial velocity is 27.8 times 2 plus 2 times acceleration, which is minus 0.588 times displacement, which is 100 meters according to the question. The final velocity is 25.6 meter per second. So this is part A and this was part B. As you can see, I used this equation here because there is no information about time. It says after 100 meters. That's why I choose this equation. And yeah, there you have it. The car slows down to 21.9 meter per second after 10 seconds and to 25.6 meter per second after traveling 100 meters up the slope. This problem beautifully illustrates how physics allows us to predict motion using some simple principles and calculations. Ever wonder how this applies to roller coasters or even your bike going up a hill? Share your thoughts and let's discuss the physics of everyday life. Let's go to the next questions. Let's roll into question 5, where we have a playful scenario. A girl rolls a ball up an incline and watches it return. The ball accelerates down the incline at a quarter of Earth's gravity. Our task is to find out how far the ball travels up the slope and how long it takes to come back to her. When the ball is released at 4 meters per second, it slows down due to the uphill climb. It's fighting against gravity and decelerates at 0.25 g. So again, ask yourself to see if it is a constant acceleration question or not. It is a constant acceleration question. Why? Because here it says constant. The acceleration is constant. So it's a constant acceleration question. It's easy. It means you can use one of those 3 equations that I mentioned. So the deceleration is, according to the problem, is 0.25 g or 0.25 times 9.81, which you can calculate it later, and it is downward. Right? To find the distance it travels before stopping, we use one of those kinematic equations. Since we know we have nothing about time, It means we can use this equation, v squared equals v naught squared plus 2a times displacement. Right? We have the initial velocity here. It is 4 meters per second. We have acceleration, and we have the final velocity. You may ask, where is the final velocity in the question? The final velocity is 0 because when the ball reaches at this point, at this exact point, velocity is 0 because after that point it starts to roll back, right? So we have the final velocity, we have everything that we need for this equation, but displacement which we need to calculate it. So we can write 0 equals 4 squared plus 2 times 0.25 times 9.81. Is it correct? No. This is not correct because we missed the negative sign here. Right? It should be negative because it's downward, right? It's in the other direction. It's fighting against gravity. So you can solve this and you will find displacement is 3.26 meters. But what about the time? How long does it take to come back to her? Well, the time it takes to go up is the same as the time to come back down because acceleration is constant. And we can find the time for the uphill trip with the equation v equals v naught or initial velocity plus at. So v, for the second part, we can write v equals v naught plus at. This time, since we have nothing about displacement, I choose this equation to calculate the time. Right? So again, 0 equals 4 plus, or let me write negative for the same reason, 4 minus 0.25 times 9.81. And this one, according to this one, time will be 1.631 seconds. 1.631 seconds. But this is not the total time. It's the time that it takes for the ball to reach this point here. So we need to multiply it by 2 because it goes up and then it goes back. So the total time, let's call this one t up. So the total time is 2 times t up, which will be 3.26 seconds. And there you have it. The ball travels 3.26 meters up the hill and returns in 3.26 seconds. It's fascinating how gravity plays with motion, isn't it? You can try this out yourself with a ball and a slope. Just be careful with the math. Experiments like these make physics tangible and fun. If you have a ball and a slope, give it a try and see if your results match ours. Let's go to the last question. All right, We've reached the final challenge of tutorial 2, question 6. We've got a motorcycle that starts from a standstill and it's initially accelerating at 3 meters per second squared. But as it moves, the acceleration changes as shown in the graph. Our mission is to figure out how fast the motorcycle is going after it's traveled 200 meters, and also to determine the rate of which its speed is changing at that point. This graph shows us how the motorcycle's acceleration isn't constant. It increases at first, then decreases. To find out the speed at 200 meters, we can't just multiply acceleration by time because the acceleration isn't the same the whole way through. So again, it's not a constant acceleration question. So you cannot, for example, use this equation, right? This is not acceptable. This is just for constant acceleration questions. Instead, we'll look at the area under the acceleration distance curve. So this is acceleration distance, and we need to look at this area under this curve, right? So let me brush it for you. So we need to look at this area. This area is key. It tells us the total change in velocity. Why? Because in physics, the acceleration is the rate at which velocity changes. When we add up all these changes over the distance traveled, what we're doing is integrating acceleration with respect to distance. So we calculate the area under the curve up to the 200 meter mark, which involves a bit of geometry and algebra. It's essentially finding the sum of the little bits of speed the motorcycle gains as it travels each meter. This gives us the velocity change directly. So the area under the curve, under the acceleration distance curve, is integral from 0 to v dv. This integral will be 1 over 2 v squared. This is how we calculate integrals. You may ask why this one is 0. This is initial velocity, right? Initial velocity is 0 because it says a motorcycle starts from rest. So this means our initial velocity is 0. And this is how you calculate this integral. So the integral of v is 1 over 2 v squared. Now let's calculate the area under the curve. So the area from 0 to 200. There are many ways to calculate this area, but as you can see here, you can calculate these two areas and add them together to find the whole area, right? In order to find the area of this shape, you need to write like this: 3 plus 6 over 2 times 100. So this is for the red one, for the red area. So this one is 3. This one, this side is 6. you add them together, divide them by 2 and multiply by. And for the green area, you can do the same. You can pause the video and calculate by your own for practice. It is 6 plus 4 divided by 2 times 100, right? Because this guy here is 4. Again, this side is 6, and this distance is 100, right? So this one is 100. So finally, the area is 950. Which means 1/2 v squared equals to 950. Just a quick reminder, the area, this is the area under the curve. We calculated the area under the curve, which is 950, and we want to find the velocity. So velocity, if you do the math, you will find velocity here is 43.6 meter per second. All right. And it asks for value of derivative dv over ds. You remember this guy, a ds equals v dv, one of the equations that we have. So it means ds over the v, or let me write in this way, dv over ds is a over v. It's simple now. So a, what is a? Acceleration at that point is 4 at 200 meters. Here, you see, it's 4. And velocity, we just calculated, which is 43.6, and the final result will be 0.0918. So rate of change of velocity with respect to distance is 0.0918. And there you have it. From 0 to 43.6 meter per second, we've used the area under the curve to unlock the mystery of motorcycles' speed. It's fascinating how graphs can tell us so much about movement, isn't it? That's the end of tutorial 2, and what a journey it's been. From rolling balls to motorcycles, we've seen how objects speed up, slow down, and everything in between. Think about how this applies to your own experiences with motion, and let's keep the conversation going in the comments. Thanks for joining me on this physics adventure, and I'll see you next time for more exploration into the world of dynamics.